All right, so let's draw some water. We know water is H2O. Oxygen has 6 valence electrons. All right, it's gonna look sort of like that. 2 hydrogens. Okay, let's talk about the shape of it and all that. What's the AXE pattern for this? Good, it's AX2 because there's 2 atoms attached to the central atom, and then there's 2 pairs of electrons, so that's E2. What's the shape for this? Good, bent. And then what's the angle? Good, 104.5 degrees. All right, now let's talk polarity. All right, what's oxygen's number? 3.5. What's hydrogen's number? 2.1. All right, we're going towards the oxygen in both directions. All right, what's the difference between them? 1.4, so it's potentially polar, right? We say potentially polar just to make sure that the actual shape of it doesn't cancel out, that it actually ends up being polar. All right, so we have this. They're both going towards that oxygen. So we can see here, if we were to cut it in half, this side of it would be slightly negative. This side of it would be slightly positive, right? All right. And you can draw the lowercase deltas right next to the hydrogens as well. That's fine. All right, so you can put them there. All right. Now, the new thing with this is, let's draw another water molecule, all right? I want to draw another water molecule right next to this hydrogen. So right here, another water molecule. What would I draw closest to that hydrogen? Oxygen. An oxygen. Yeah, exactly. Why? Yeah, okay. So we have our oxygen, hydrogen, all that again. And we already know the dipoles, so we can just kind of put them in there. Slightly negative, slightly positive. Okay? So we can see there's opposite charges here, right? And they're going to attract to each other. Now, this is a dipole. This hydrogen with a positive, slightly positive charge. This is another dipole. This oxygen with a negative charge. So a dipole-dipole interaction means you have 2 dipoles. They're on different molecules and they're interacting with each other. All right, they're attracting each other. All right, so that would be a dipole-dipole interaction. This one is a special dipole-dipole interaction because it's between hydrogen and something else. And that's what we would call a hydrogen bond, all right? Because there's an attraction between a hydrogen that's slightly positive and then an oxygen that's slightly negative, all right? There's one other way to represent this that you should know. Just like you have lines here to represent bonds, for a hydrogen bond, you actually would draw a dotted line between the 2. So you'd have it between the oxygen and the hydrogen, and you wouldn't want it to look like electrons. You just kind of want to make it look more like that, so we know it's not just extra electrons, it's a dotted line connecting these 2. This bond is weaker than this. Covalent bond is much stronger, but this is an important bond. It's what holds the 2 helixes of DNA together. A lot of properties of life and whatnot are reliant on this hydrogen bonding, all right? Another thing with the hydrogen bonding is if you had like a glass of water and a glass of acetone, I don't know why you'd have these 2 things, but if you had them out and you left them out for a while, the water would evaporate slower than the acetone because the acetone would have less of these hydrogen bonds holding it together. So it actually helps hold water on Earth as well, because if it didn't have these hydrogen bonds, it would evaporate much quicker. All right? Any questions with any of that?